Hello and welcome to this video lesson on shapes of molecules. It has specification reference 3.1.3.5 and here are the learning objectives. Just one in fact. We want to be able to predict the shape of single molecules and molecular lines from the bond angles, and we want to do that for molecules where there is a central atom that has up to 6 electron pairs surrounding it. So from very simple molecules, the shape of those, to quite complicated molecules. But the first thing we need to know how to do is how to draw 3D shapes on a 2D page. So I'm going to demonstrate this with a methane molecule, which you know is CH4. All right, so we're going to draw a methane molecule CH4, and in 3D, of course, it's got 4 bonds, and one of them it's going to be a trigonal pyramid shape. Okay, so one of the hydrogen bonds is going to come out the page, and the way that we draw that is a little sort of triangle that's filled in like that, and that's going downwards and coming out the page when it's drawn like that. And then when we want another bond that's going back into the page, and we draw that with sort of triangle with hatch lines in it, and so that illustrates another bond. There's one bond that is at this angle, but it's in the plane of the page, and so it's just a normal straight line. And there's another bond that's also in the plane of the page, but vertically up, and we would draw it like that. So that's how you would draw a 3D picture of a methane molecule, where this atom here is coming out of the page and that atom there is going into the page. And the first step to working out the shape is to find the number of electron pairs. And what we have is a 6-step process to memorize, and once we've memorized that, we just go through it, and that will help us draw the molecule. So the first step is to find the central atom. Okay, so if again we're using the methane molecule, whose formula is CH4, and the displayed formula, 2D displayed formula, you could draw it like this. Okay, so we'll use that as the example, and of course the central atom is the carbon atom. And then the next step, after you've done that, is how many electrons in the outer shell. Well, carbon is in group 4, and so it has 4 electrons in the outer shell. So we'll just put a little 4 down there, and then we can move on to the third step. That's actually moved us on to a few more steps as well. So anyway, the third step, we add 1 electron for each atom that the central atom is bonded to. So this is the central atom, and it's bonded to 1, 2, 3, 4 hydrogen atoms, and so we're going to add another 4 to that, so that would be 8 in total. And if it was an ion, which is not of course, you would adjust for the charge. So for example, with NH4+, for example, is a molecular ion, and that has a positive charge, which means it's lost an electron. So you would subtract 1 for the NH4+, whereas let's say you were trying to draw SO4 2-, you would add to that, because the SO4 2- has got a 2 negative charge, which means it must have 2 extra electrons. But in this case, we don't have to make any adjustments because it's not an ion. And so then the number of electron pairs is this total, which was 8, which was the total of our 4 and 4. And it's that total divided by 2, so 8 over 2 equals 4. So there are 4 electron pairs in this methane molecule. And let's decide which of these electron pairs are bonding pairs and which are lone pairs. So out of these 4 electron pairs, the bonding pairs Well, we see we've got four bonds, so we've got 4 bonding pairs, which must mean there are 0 lone pairs. So there we have it. We have noticed in the methane molecule there are 4 bonding pairs of electrons, no lone pairs of electrons, and so now we can go on to work out the shape of that molecule. So once we've got the number of bonding and lone pairs, we can use the following table to work out the shape. And we have, as you can see, there's 12 rows here, and so there's going to be 12 shapes for you to remember. I can hear the groans from here, but don't worry, it's not as difficult as it may at first seem. So if we have just 2 electron pairs, and if we have 2 electron pairs, then 2 of them are going to be bonding pairs, and the shape of that molecule will be a linear shape. So that's fairly easy. We'll have a look at an example in a minute. But first we're going to complete this whole table. So if we have 3 electron pairs, if we've used the previous process to work out those 3 electron pairs, and let's say in this case all 3 of them are bonding pairs, then the shape is a trigonal planar shape. Again, we'll look at what a trigonal planar shape is, but for now I just want to list it out. Of course, we could have 3 bonding pairs, or we could have 2 bonding pairs and 1 lone pair, in which case it wouldn't be trigonal planar, it would be a bent shape, like a bent straight line. Okay, so that's the 2 options we have for when there are 3 electron pairs, but when there are 4 electron pairs, all 4 of them could possibly be bonding pairs, in which case our shape would be a tetrahedral. That's for 4 bonding pairs, but if there were only 3 bonding pairs and the other one was a lone pair, then the shape would be a trigonal pyramid. So not a pyramid like the Egyptian pyramids, they're square-based pyramids. So this would be a pyramid with a triangular base. Okay, now we have another option for 4 electron pairs, and that would be when there are 2 bonding pairs and 2 lone pairs, in which case that shape would also be a bent straight line shape. Okay, that's that, and now we can move on to 5 electron pairs connected to the central atom. And if all 5 of them were bonding pairs, then we would, in this case, we would have a trigonal bipyramid. So that would be a trigonal pyramid, 2 of them with their bases joined together. But again, don't worry, we'll have a look at one in a minute. So, of course, if we had 5 electron pairs, 4 of which could be bonding pairs, and that would leave 1 lone pair, and the shape of that sort of molecule is called a seesaw. And we have another option, 3 bonding pairs, 2 lone pairs, and that would give a T-shaped molecule. Okay, and as we said earlier on, we have to learn all the shapes up to 6 electron pairs. And if all of those electron pairs were bonding pairs, then that would be an octahedral. That would be an octahedral shape. But if, in contrast, you only had 5 bonding pairs and 1 lone pair, that would be a square pyramidal shape. And that is like the Egyptian pyramids. And the last option is if there were 4 bonding pairs and two lone pairs, in which case this would be called a square planar. So there are all the shapes, 12 shapes for you to remember, and their corresponding numbers of bonding pairs, lone pairs. Let's have a look at some examples, probably one example of each one. So let's have a go at predicting the shape of some molecules using our 6-step process here and the table we had on the previous slide. Okay, let's start off with a molecule called beryllium chloride. So beryllium chloride is in group 2, and so the formula is going to be BeCl2, and we're going to first of all, step 1 is going to be the central atom. The central atom is our beryllium. How many electrons in the outer shell? Well, it's in group 2, so there's going to be 2 atoms in the outer shell. How many atoms is the beryllium bonded to? That's another 2. All right, so those 2 added together makes 4. We don't have to make any adjustment for it being an ion. It's a molecule. And then we're going to take the 4. 4 divided by 2 equals 2. And because we know we've got 2 bonds, both of those electron pairs. So we've got 2 bonding pairs and no lone pairs. So if we've got 2 bonding pairs and lone pairs, we refer to our table. And then what I can do is I can do this. I can say, we could read off that table that if we've got 2 bonding pairs, the shape of the molecules with 2 electron pairs is linear. Okay, so in which case we could then draw this molecule as a beryllium chloride. So that's linear because it's in a straight line. And our bond angle would be 180 degrees. So before we go on to predict the shape of a different molecule, some of you may have spotted something strange about beryllium chloride. Beryllium being in group 2, I'm sure some of you expected this compound to be ionic when in fact it's molecular. And so that's perhaps a topic for class if you want to remind me to discuss that in class with you. So the next example we can do, why don't we do boron trifluoride? So let's boron trifluoride. As the name suggests, the formula of it is going to be BF3, like that. So our central atom is going to be boron, which you look up to see that's in group 3, so 3 electrons in the outer shell, and we've got 3 fluorine atoms joined to that, bonded to that, so that's another 3. Add those together, we get 6. It's not an ion, so we don't make any adjustment for that. We take our 6, we divide it by 2 equals 3 electron pairs, but we've got 3 bonds, so we've got 3 bonding pairs and no lone pairs. So we've done step 1 of the process. Step 2 is to refer to our table, which we will have memorized. And when we look at our table, we can see that the shape of molecules with 3 electron pairs is trigonal planar or bent. So it's trigonal planar when there are 3 bonding pairs and no lone pairs, and bent when there's 2 bonding pairs and 1 lone pair. So trigonal planar shape is going to look like this. So planar, as the name suggests, it's going to be in the plane. So we'll draw the molecule in the plane of the screen, and boron is going to be in the middle. It's trigonal, which suggests a triangle, so why don't we draw it like this? So we're using straight lines for the covalent bonds, no triangles or hatched triangles, because these bonds are in the plane of the screen, and so our three fluorines would go over like that, and that is a trigonal planar shape. And let me just say that for the previous slide, for the trigonal planar shape, the bond angle, of course, is 360 degrees divided by 3 angles there, which is 120 degrees. Okay, and the other option for 3 electron pairs is when there are 2 bonding pairs and 1 lone pair, in which case we get a bent molecule, and we're going to have a look at that later. But for now, we're going to have a look at a different example. We're going to have a look at the ammonium ion. We're going to predict the shape of the ammonium ion. And you'll probably know that the formula of ammonium is NH4+. And going through our 6-step process, our central atom is our nitrogen, and that's in group 5. So 5 electrons in the outer shell. We're going to add 1 electron for each atom in the central that the nitrogen is bonded to. So that's 4. So they add up to 9. And we have to adjust for charge now, because this is an ion. This is a positive ion, so that means we must have lost 1 electron, so we're going to subtract 1. So that's going to give us 8. And then we're going to divide that by 2, because these electrons are in pairs. So 8 divided by 2 equals 4. We have 4 electron pairs. And we have 4 bonds. So each one of those electron pairs must be a bonding pair. So we can say we've got 4 bonding pairs and no lone pairs. Okay, so now we know that it's 6, so it's 4 in total, and all of those 4 are bonding pairs. We can refer back to our memorized table, and if we did that, we would get this information. So shapes of the molecules with 4 electron pairs is either tetrahedral, trigonal pyramidal, or bent. This is the option for 4 and 0, 4 bonding pairs, 0 lone pairs. And so what we need to do is we need to draw our ammonium ion as a trigonal pyramidal, as a tetrahedral shape. So let's draw it here. Here we've got our nitrogen. We're going to put our positive charge on our nitrogen, and a tetrahedral shape is going to be drawn like this. So we've got one of the bonds coming out of the screen, so we draw that as our filled-in triangle, like so. And we're going to draw our hydrogen on that. We've got one of our bonds going back into the screen. We draw it like that, sort of hatched triangle, and we draw our hydrogen on the end of that. And our third one is in the plane of the screen, so we just draw it as a straight line. And we've got a coordinate bond as well. If you remember when we studied the ammonium ion, we have a coordinate bond which we draw as an arrow to the other hydrogen atom at the top there, and that's a tetrahedral shape. So that is our prediction of the shape of the ammonium ion. What we might do now is something that will give us one of these shapes, but we'll have to see how that works out. But before we go, let's just highlight the bond angle, which is what I forgot to do on the previous slide, of course. So the bond angle, this angle between these bonds here, and they're all the same. This one is 109.5. And bear in mind that you need to remember these bond angles. So it's quite a tough lesson to remember for all of the stuff that needs to be remembered, but conceptually I think it's easy enough. So let's do another example. Let's predict the shape of ammonia. So ammonia, and you know the formula of ammonia is NH3. So going through the same process as before, our central atom is nitrogen, and nitrogen group 5 electrons in the outer shell. Add 1 atom for each of the other atoms, that's 3, so that makes 8. It's not an ion, so we don't have to make any adjustment there, and so 8 divided by 2 equals 4. Okay, and so then we're going to split those 4 into, we've got 3 bonds, so they're going to be 3 electron pairs that are bonding pairs, 3 bonding pairs, which leaves 1 lone pair. So what we've got now is we've got a molecule that has 4 electron pairs, 3 of which are bonding pairs and 1 of which is a lone pair. So we refer back to our memorized table, and we get this one again, and what we see from the table is that when we do have 4 electron pairs, 3 of which are bonding pairs and 1 is a lone pair, the shape that we need to draw is a trigonal pyramidal shape. So we're going to make that ammonia into a trigonal pyramidal shape. So starting off as usual with our central atom, we've got our nitrogen there like that, and trigonal pyramidal is sort of like an Egyptian pyramid, but with a triangular base, not a square base. So in 3D, of course, we want one of the hydrogens to be coming out of the screen, like that. One of the hydrogens to be going into the screen, like that. And one of the hydrogens is in the plane of the screen, like that. So there are our 3 bonding pairs of electrons, and of course we still do have our lone pair, which we draw above the nitrogen like that. So that's our ammonia molecule, and we've drawn our 3 bonding pairs and the 3 bonds, and we've drawn our 1 lone pair as well. And if you remember from some time ago, we discussed the effect on bond angle of lone pairs versus bonding pairs, and so these bonding pairs have the charge cloud that is spherical. Let's draw a little, that's supposed to be a sphere, whereas these charge clouds are sort of longer stretched shapes, and what that means is that the bond angle gets squished up. This bond angle gets squished up compared to, say, for example, the previous example, which was the ammonium, which was more of a symmetrical shape. So this bond angle is 107. You remember in ammonium it was 109.5. So this is 107 degrees because of the different shapes of those charge clouds. So now we're going to have a look at predicting the shape of the water molecule. So water, as you know, is H2O. And I'm just going to do this in slightly different order. You'll see why. Water is an example of a bent shape, right? And the bent shape comes from, there's 2 different configurations of electron pairs that give a bent shape. So when there are 2 bonding pairs and 2 lone pairs, right? So we can have 2 bonding pairs and 2 lone pairs. And we've got 2 and 2, so that's 4 electron pairs in this example. And you might remember I skipped over another example that of a bent shape, which was 2 bonding pairs, right, and 1 lone pair, when there were 3 electron pairs in the molecule. And both of these combinations give a bent shape. So we can use one example, that is water, to illustrate this bent shape of molecule. Okay, so that said, let's still go through our process here. Our central atom, hydrogen. How many electrons in the outer shell? 1. Add 1 electron for each of the. Let me pause. Let me just backtrack on that. I realized I've made a mistake. So the central atom, of course, is oxygen, and oxygen's in group 6. So 6 electrons in the outer shell. We've got 2 hydrogens attached. So together they make 8. It's not an ion, so we don't adjust that. And 8 divided by 2 equals 4. And we've got 2 bonds, so that means we've got 2 bonding pairs, and we've got must then therefore have 2 lone pairs. So that's our combination, and when we have that combination of 4 electron pairs, and 2 of which are bonding pairs and 2 of which are lone pairs, then the shape of our molecule is a bent shape. So now we have to draw this H2O molecule as a bent shape. And so we're going to draw the oxygen in the middle, and it's going to be bent, which means that we're just going to draw it, right? Not as a straight line, but as a bent line like that, because not only do we have our 2 bonding pairs, but we also have 2 lone pairs, which we're going to illustrate like that. And so that's how it looks. And you remember the charge clouds that are the lone pairs force the bonding pairs, repel the bonding pairs and repel each other, such that the bond angle there between the 2 hydrogen-oxygen bonds is actually 104.5. So that bond angle there is 104.5, which you do need to remember. And the next example we're going to predict the shape of is phosphorus pentachloride. Phosphorus penta, so that will be 5. Phosphorus pentachloride, so that's going to be P for phosphorus, Cl5. Okay, so going through the same process, central atom is going to be a phosphorus atom. And phosphorus is in group 5, 5 electrons in the outer shell. Add 1 for each of the chlorides, that's 5, so together that makes 10. No ionic adjustment. Divide our 10 by 2 gives us 5. We've got 5 bonds, and so that's going to be 5 bonding pairs and no lone pairs. And when we've got 5 bonding pairs and no lone pairs, we look at our table, our memorized table, and we get this information. The shape of the molecules with 5 electron pairs is either trigonal bipyramidal when there are 0. So this option here is for 5 bonding pairs, 0 lone pairs, and seesaw and T-shaped are for 4 and 1 and 3 and 2. So we're going to draw a trigonal bipyramidal shape for phosphorus pentachloride. So we're going to draw our phosphorus atom in the middle, and the trigonal bit we draw as a triangle. So when we've got a triangle in the plane that is perpendicular to the screen. So we're going to have 1 chlorine straight to the right, and that bond is in the plane of the screen. We want 1 chlorine atom that is coming out of the screen. So we're going to fill that in, and we've got 1 chlorine atom that is going into the screen. We're going to draw it like that. So that's supposed to represent, and let me just change color into a little light color. That's supposed to represent a triangle that is in the plane that is perpendicular to the screen. So that's 3 of our chlorines, and what we need to do is account for the other 2, and so it's a trigonal pyramid. So the first pyramid is the pyramid that has the point at the top. And so if I just go back to my light blue, I wonder if you can imagine a pyramid, the edges of which I've attempted to draw there. So that's the pyramid with the point at the top, and the pyramid that is the bipyramid, the second pyramid, uses the same base, but the point of the pyramid goes vertically downwards, so points downwards. So we draw that like that, and so that is a trigonal bipyramidal shape with the 1 phosphorus and the 5 chlorines. But just before we go, this molecule is odd as well, because phosphorus is bonding covalently there, but it's not getting a full outer shell, is it? It's going to get, it's offering up 5 outer electrons, which is all 5 of its outer electrons, so they're all getting paired up, but we're going to have 10 electrons altogether. And we can discuss that molecule in class if we want to go a little bit further than the A-level spec. And the next example we're going to look at is sulfur tetrafluoride. I'm going to predict the shape of sulfur tetrafluoride. So tetra, you'll work out, is 4. So that's going to be SF4 is our formula, with the central atom being sulfur, sulfur being in group 6. So we're going to add 4 electrons, making 10. No adjustment for the ions. 10 divided by 2 is 5. But we've only got 4 bonds, alright, so that's going to be 4 bonding pairs and 1 lone pair. So when we have 5 electron pairs, 4 of which are bonding pairs, 1 of which is a lone pair, then we refer to our memorized table, which tells us that we need a seesaw shape. So now I'm going to draw this seesaw shape for sulfur tetrafluoride, and then you'll know it. So again, we want to start off with our sulfur in the middle, and the seesaw shape looks like this. You've got, it's like a vertical seesaw, I suppose, with 2 of the fluorides at the top and the bottom of that, and you've got another fluoride coming out of the screen, and another fluoride going into the screen, and our lone pair on the other side of the sulfur with its spherical charge cloud forcing the other bonds to get closer to each other. And this is a 3D shape, remember, so the bond angles, which we've been drawn in green, we can write down here. So this bond angle here is 86.5, and this bond angle here is 102 degrees, and that's called a seesaw shape. And I think what you can guess is coming up next is a T-shaped molecule, but let's see. Let's try the example of chlorine trifluoride. Chlorine trifluoride, which is going to be ClF3, tri being 3 of course. So our chlorine trifluoride, let's go through our process as usual. Central atom is going to be the chlorine. Chlorine's group 7, add 3 makes 10, no adjustment for ions. 10 divided by 2 is 5. We've got 3 bonds, so that's going to make 3 bonding pairs and leaving 2 lone pairs. Okay, so when we get 5 electron pairs in total, 3 of which are bonding pairs, 2 of which are lone pairs. Then our memorized table tells us that that is a T-shaped molecule. And this is an easier one to remember because it does sort of look like its name. And so we'll start off with our chlorine again. We've got to draw 3 fluorines in a T. It's not quite a proper T because we're going to draw the fluorines at a slightly non-straight angle because we've got 2 lone pairs. And the 2 lone pairs are going to be drawn on this side of the chlorine, like that. So you can see it's sort of a T if this bond angle here was 90 degrees between the chlorine and the fluorines, then it would be a proper T, but it's not actually 90 degrees, it is 87.5 degrees. So there you are, that's a T-shaped molecule example that we've predicted. I think you can guess we're now moving on to the last trio of shapes, and they're the 3 shapes for 6 electron pairs, but let's go through the same process. Our first example is going to be sulfur hexafluoride. So sulfur hexafluoride. Sulfur hexafluoride, and we can work out that it's going to be S and F hexa is 6, like that. Sulfur hexafluoride. So let's work out strictly what shape it is from the number of bonding pairs. Sulfur is our central atom. Sulfur is group 6, 6 electrons plus 6 fluorine bonds is going to be 12 altogether. No adjustment for ions. Number of electron pairs divided by 2, so that's going to be 6. And we've got 6 bonds, so that's going to be 6 bonding pairs and no lone pairs. So when we have 6 and 0, we refer to our memorized table, and we've got 6 electron pairs, and octahedral is the shape for 6 bonding pairs and no lone pairs. So we're going to draw an octahedral shape. And an octahedral shape looks like this. We're going to have our sulfur in the middle, and we're going to have a square that comes out of it's going to be the plane of this square that we're going to draw is the plane that is perpendicular to the screen. So it comes out of the screen and goes into the screen. So our first fluorine is going to come out of the screen, and it's going to be on this corner of the square here. Our second fluorine is also going to come out of the screen. So we draw this, right, and that's going to occupy that corner of the square. Our third fluorine is going to go into the screen. It's going to occupy that corner of the square. And our fourth fluorine is going to, so can you see that's a square? Hopefully you can see that we've got a square here, like that, where the top 2 fluorines go back into the screen and the bottom 2 fluorines come out of the screen, like that. And then it is an octahedral shape, which means that we've got another fluorine. The 5th fluorine comes vertically up, the 6th fluorine goes vertically down, and so it's octahedral because we've got 8. If we joined all those up, we would have 8 faces of a shape, which is why it's called an octahedral shape, and that's how you draw it. And if we want to look at another example, we might want to have a example of a square pyramidal one, which would be for when there are 5 bonding pairs and 1 lone pair. So let's maybe have a look at that next. So we're going to have a look at the example of chlorine pentafluoride. That's going to be Cl for chlorine, and 5, penta is 5 fluorides there. And if we went through our normal process, we would find that we would have 5 bonding pairs and 0 lone pairs. Sorry, 5 and 1. 5 and 1, yeah, making 6. Okay, and this was 6 and 0, this is 5 and 1. So we want to draw chlorine pentafluoride as a square pyramidal shape. So we're going to put our chlorine in the middle, and in the same way as we did in the previous example where we had sulfur hexafluoride, it's a very similar shape, except one of the fluorines is disappeared and replaced by a lone pair. So it's going to look like this. We're going to have one of our fluorines coming out of the page. This is going to be the front right corner of the square. This is going to be the front left corner of the square. This is going to be the back left corner of the square, and that's going to be the back right corner of the square. So that square is supposed to come out of the screen and go back into the screen. And then we've got our 5th fluorine vertically above, and our lone pair is vertically below. And that's called a square pyramidal shape. And you can see that if the square is the base of the pyramid and the top fluorine is the point of the pyramid, that looks just like an Egyptian pyramid. So square pyramidal is the predicted shape for chlorine pentafluoride. And next we're going to have a look at a square planar example, and so that would be when there were 4 and 2, so 4 bonding pairs and 2 lone pairs. And the example of that shape is xenon So xenon tetrafluoride. So xenon tetrafluoride, you thought that noble gases didn't make compounds, so they do, at least xenon does. And xenon tetra is 4, so we can see it's XeF4 is the formula. And we go through this usual process again, and we're going to come out with 4 bonding pairs and 2 lone pairs. So we're going to have 4 bonding pairs, 2 lone pairs, and then we refer to our memorized table, and we can see that when it is 4 and 2, then it is a square planar shape. Okay, and so we start off with our central atom, which is our xenon atom, and that's going to be bonded to 4 fluorines, which are the corners of the square that's referred to in the name. And it's a square that is drawn into and out of the plane of the screen, like before. Okay, so we're going to draw for top right, top left, coming out of the screen like that, and then going back into the screen like that. Okay, so that's our square that's supposed to be perpendicular to the plane of the screen, and our lone pairs are top and bottom this time. So there's top and there's bottom. There are 2 lone pairs, and so that's a square planar shape drawn like I've drawn it there. And the bond angle here is going to be 90 degrees, like that. And the last thing to note before we finish is to see what happens when there are double bonds, because you will have noticed that up till now all of the bonds that we've been dealing with have been single covalent bonds. But for example, let's have a look at carbon dioxide, which you will probably remember has double bonds. Carbon dioxide CO2. You'll have drawn that at GCSE like this. and that's a linear shape. And what you can say about double bonds is that we're going to treat them, as far as shape is concerned, pretty much like as if they were single bonds. So the bond angle here is 180 degrees. So that bond angle is 180 degrees. But when there is a lone pair involved, like for example in sulfur dioxide, so in sulfur dioxide, SO2, yes, in sulfur dioxide there's a lone pair as well, so it sort of looks like the water molecule. It looks like this, with two double bonds between the sulfur and the two oxygens, but there's also a lone pair, one more lone pair up here. And if we would just, let me draw a vertical line to represent what would be a normal covalent bond, and so you might expect the bond angle to be 120, 120, 120, but then you remember that lone pairs modify the bond angles, so they might mean that this bond angle here becomes less than 120 because it gets squished together by the spherical shape of the charged cloud that is the lone pair. However, these are not single bonds. That does happen with single bonds, but these are double bonds, and so the charge density of a double bond is a bit deeper. So it's not as sort of elongated, and that cancels out the effect of the repulsion from the lone pair. So in fact, the bond angle between the sulfur-oxygen double bonds is 120. They sort of balance each other out, so that's 120 degrees for sulfur dioxide. And you'll see that the actual name for that shape will be bent. So that's it for this video lesson. A lot of memory work involved, I'm afraid, but you just got to get to it. So as usual, to finish, we will just recap the learning objective. That was to be able to predict the shape of simple molecules and molecular ions. We did NH4 at least, NH4 plus, we did ammonium ions, and we did several molecules with up to 6 electron pairs with various combinations of lone pairs and bonding pairs. And so we predicted about 12 different shapes.